So after we have calculated, we've graphed the histogram, we've done the frequency polygon, we've kind of reset the axis so that we're now looking at relative frequency rather than the raw frequency by dividing the class frequency by the total sample size. Now we want to construct a cumulative frequency distribution or a cumulative distribution function. So how do we construct a CDF? So what we're going to do is we're going to kind of start a new table real quick, and we are going to say, okay, what if the profit was less than 600? What is my cumulative frequency? So we know that relative frequency is the class frequency divided by the n, right? But what is this cumulative frequency, right? Well, for the first one, it's the same thing, which is somewhat confusing. So for the first one, the cumulative frequency is 8. And the way that we find this is we just take 8, right? We see that there's nobody making between 0 and 200. So I guess we could put 8 plus 0. How about that? Because in a way, that is the next part, right? Less than 600 is not just the 200 to 600 category, it's also the less than 200 category. Yes, we don't have any observations of the less than 200 category, but that doesn't mean that the less than 200 category doesn't exist. It doesn't exist when we show it on the histogram, but it still exists. So it's 8 plus 0, because it's all of the categories, right? This is our 200 to 600 frequency, and this is our 0 to 200 frequency. Is that making sense to everyone? All right. So the next one is going to be, what if profits are less than 1,000? Profits are less than 1,000, our cumulative frequency is 19. How do we get that? Well, we're going to add 11 plus 8 plus 0. So now we're going to add the 600 to 1,000 in addition to the 200 to the 600 in addition to the 0 to 200. So we add all of the raw frequencies of all of the categories below whatever that particular row is. Making sense? Making sense, everyone? Nods? Nods? Head nods? Okay. So we just keep doing this. Less than 1.4, less than 1.8. So go ahead and do this on your own. Make sure that you're understanding, and check your numbers with me as I throw them up here. Oop, missed one. 38. Yes. So I got a little lazy. And I just started to add the numbers to the last size, right? Nothing wrong with that. So does that make sense, everyone, how we're getting these cumulative frequency numbers? Okay. So, step 2, so this was step 1. What is the cumulative frequency? Step 2 is convert to cumulative relative frequency. So I know, seems a little scary, but we are just doing the same thing we were doing last time. So last time, right, in order to get the relative frequency, we took the class frequency and we divided by the n, right? The numbers that we had here, 8 divided by n, 11 divided by n. So now we're taking the cumulative frequency numbers and we're dividing those by n. So cumulative relative frequency is equal to the cumulative frequency divided by the number of observations. So on your own, go ahead and calculate what the cumulative relative distribution is of these categories to the right here. So this one we are going to represent in a percent format. And if you do this correctly, the way that you can check your work is, 1, is the last one 100%? And then 2, are they increasing? If they're not increasing, and the last one's not, or the last one's not 100%, you did something wrong, right? This number should be increasing. So 4% to 10% to 23 to 44 to 69 to 87 to 97 to 100, right? I almost said that it must be strictly increasing, but that is not true. When we talk about strictly increasing, that means that a zero change is not possible. But a zero change is possible in the cumulative distribution function. So now we're going to take this data and this data, and we're going to graph it to get this thing. Best way to do this. I want to get all this stuff, possibly. Move it over here. Yes. I like it. Okay. And there's a method to my madness here, and you'll see why in a bit. So this class is running long. I'm just going to finish this and do a quality job, and then I will push a video out tonight covering the first part of chapter 3, because again, it is really easy. I will stop once we get to Chekhov's theorem, because as the name suggests, it's kind of difficult. But the mean part, the median part, the variance part, the standard distribution part, I'll record some videos on it, and I'll throw it up later today. So please watch those videos before we have class on Wednesday. Okay, so let's not do blue. Thank you, Friday. Yes. Yes. What day is it? Where am I? All right. So let's stick to green here. Oh, let's label our axes first, though. How about that? Okay, so over here we're going to have the percent of vehicles sold. And down here, we're going to have our profit. Get rid of this guy. And so we start at 200. So for this one, we're going to be we have 200 here, and at 200 or less, we have 0. So there's 0% of vehicles sold at 200 or less. Now, then we have at 600 or less, which is going to be here. At 600 or less, we have a cumulative relative distribution frequency of 4.4%. And now you will note this is the only value that is going to be the same on the CDF as on the PDF, right? We find this value here. It's moved around a little bit because we're in a histogram. So it's kind of on the 400, if we want to be real technical about it. But the meaning is the same. Under 600, 4.4%. Between 200 and 600, 4.4%. So this is the only one that's going to have the same value on the two graphs. So now the CDF builds upon the earlier work, and so now the next value is at 1,000, and it's not just that 4.4%, and it's not just the 12.8% of the next bin, but it is the combination of those two, right? It is the 19 out of 180, it is 10.6%, less than 1,000. And then we keep going. The next one is at 1,400, and this one corresponds to something like 23%. And so this continues on, and actually I need to draw this a little bit more to scale. Apologies, everyone. Got to be monitoring of my room here. So we'll do that, 10.6% there, 1400, 23.3% here, because this is climbing ever higher, right? 1800, 2200, 2600, 3000, 3.4. And one of the things that we do know is that at 3.4, right, this was one of our checks. At 3.4, it needs to be 100%, right, the maximum of our graph. So in a way, I've mislabeled this graph because I put an arrow at the end of this graph. This graph does not need an arrow, right? We don't have to go beyond 100%. We can end this graph right there at 100%. And so graphing these values in the middle, less than 1800, we have 44%. And again, these are not drawn to scale. We've got 69%, 87%, 97%. And so we end up with something that looks like this. So something with a positive slope that has this vaguely S shape to it. I didn't draw it terribly accurate, but there should be probably more of a curve to it, like that. And so this is telling us all of the companies that made $1,400 or less. There were 23% of the sampled companies that made $1,400 or less. What else can we infer from this graph? From the data that I have on this board, we can infer three more things.
The slope of the line increases faster at the middle, which means we know that our distribution is predominantly centered in the middle.
Very good.
And then the slope decreases around the edges, so we can see that's a relatively normal distribution.
Right. So the fact that we have something that starts off with a relatively minor slope here, that has a steeper slope here, right? And so again, remember, slope is just that rise over run. Sorry. Can you tell I'm tired? Rise over run. And we can tell that down here, the run is much greater than that rise, right? And so we can tell that the slope is changing from something rather low here to something rather high here, and then back to something rather low here again. And that is characteristic of the PDF, the probability distribution function. There is a low likelihood of finding yourself in the 200 to 1,000 region and finding yourself in the 2,600 to 3,400 region. There is a high likelihood that you're in this bulky middle here. So the shape of our PDF directly leads to, the PDF determines the shape of the CDF. So they are inextricably linked in the same way that an exponent is a logarithm. A PDF is the rate of change of our CDF. So if we were to take an integral, which I know a lot of you are like, ew, gross, but if we were to take an integral from 0 to 1,400, so if we were to look at the area underneath the curve here, we would find that that corresponds to a value of 42. Answer to life, universe, and everything, right? And that 42 corresponds to, if we look at this other axis here, and this other axis is the cumulative frequency. we would find that this 42 number, which is the integral, the value under the curve of our probability distribution function, corresponds to the number of cars in the cumulative distribution function. So our cumulative distribution function is going to tell us the area under the curve of the probability density function. And this 42 cars, obviously, that's how we got our 23% number. We took 42 and we divided it by 180 and we multiplied it by 100. So questions on the link between these probability bins and the cumulative distribution graph. This is the heaviest and most heady conceptual thing we'll probably learn in this class. That's why I'm trying to take it like slow so that we understand that like these things are linked together. The only way a CDF changes for a PDF to change, vice versa. Okay? Awesome. All right, I'll see you all in class on Friday.